oxygen is 5. So mathematically, this part and this part stayed the same because we're still going to P2O5. So anything that had P2O5 in it does not need to change. Only thing we need to change is anything that had P4, we need to change to oxygen. And so this is going to come out to be 284. So now we have how much product we can make starting from each amount. All we have to do is look at those two numbers and say which one is smaller. Which one is smaller?
P4.
The P4 number. What people like to do, even though it's wrong, is what they'll do is they'll write this out and then they will say limiting reactant. That is not the limiting reactant. That's not even a reactant, that's a product. That is your limiting reactant. It's the reactant that gave you the smallest amount of product. So don't do that. If you want to just write an arrow, you need to do that one. Or what I suggest is make it as clear as possible and just say P4 is the limiting reactant. Something like that. Now, if there was a subpart, A2, that said how many grams of product can you make, you already did it. It's 142 grams. And so you already did the second part of the question if that part existed. So let's do part B. So in part A, P4 was our limiting reactant. Because that one we did all the way to grams, part B and C we can just stop at moles. So we're going to do 0.2 moles of P4. And we're just going to stop at moles of P2O5. One, and this is 2. So in this case, we said, well, we don't need to know our grams. So let's just figure out the moles and then compare the moles for each one. In this case, we got 0.4 moles from each. So in this case, there is no limiting reactant. They are equally proportioned. They're going to run out at the same exact time. And so if the question said, how much product can you make? It's 0.4. Because 0.4 is still the smallest number, it's just in both of them. So now let's do C. So in C, we have 0.25 moles of P4. Out to be 0.5, and then we've got 0.75.
So I'm assuming we have to memorize that.
Memorize what?
This whole equation.
This
Yeah.
thing?
Yeah.
Yes. We don't have to. if you want to use this, you have to memorize it. Otherwise, you can remember the process and then figure this out as you need it. The way I do it is I remember grams of A, moles of A, moles of B, grams of B. And so that's the units across the top. And based on dimensional analysis, if you know the units on the top, you know the ones on the bottom because they have to cancel that one. If you just remember the units across the top, the whole thing writes itself. I don't want to do 0.75 divided by 5 in my head. What's that? 0.75 divided by 5. 0.3? Times 2. I forgot, I missed the 2 times 2.
It's still 0.
Okay. So you did it right, I did it wrong. So it's 0.3. Which is our limiting reactant?
Oxygen.
In this case, the oxygen is our limiting reactant. Remember, don't just circle that. That's nothing. This is our limiting reactant. This is what we use to figure that out. Our oxygen is our limiting reactant. Let's take our break now. We'll start at 7:30 on that clock. So 12 minutes. You would just say something. There is no sodium on exams, at least in where you have to use the math. So I purposely avoid that. I will though. The Wiley thing was not your fault at all. So I would go in. I'm guessing you weren't told, and so I want to. If it's not being careful to give an answer.
No, it was just the numbers. I know numbers, right?
The problem with Wiley was somebody didn't try to take your answer. That's not something I'll go back and fix. But if there's something that's my fault,
It's not your fault. It's just.
I got to.
But how is that wrong? This is an actual periodic table.
I don't know.
Okay, cool.
Yeah. So that's the same exact periodic table that's on the cheat sheet for the final exams.
Yeah, I remember this.
And it's well. There's a copy. The final exams are not the ones that I have. They come from the department. The ones that we have are scanned copies that another professor copied from the final exam copy. So I'm thinking they scanned it before they realized there was a problem. And they fixed the final exam copies. But then there was a scanned copy from the It still had the wrong number.
Is it only the sodium?
It's almost-
I was going to change that.
From all I've ever seen was that I would go through element by element. I've never had a problem where somebody said something wrong, but sodium over and over again. I used to use sodium all the time. And then I realized it, and then I don't use sodium. on a legal sheet of paper something to tear across the top and use a blue pen.
Yeah.
Is that it? finish this slide, the next few slides are a walkthrough of what we did. Then we are on to this slide. This is another slide of limiting reactants. So we have a different reaction, and then we have a couple more situations with different amounts of reactants. You need to figure out what the limiting reactant is, and then in each case, how many moles of ammonia can be produced, which we're going to figure out when we calculate which is the limiting reactant. So let's look at A to start with. So we've got 2 moles of nitrogen, 5 moles of hydrogen. We need to do 2 separate stoichiometry problems to figure out how much ammonia each one can make. In part 2, it says how many moles of ammonia can be produced. And so in this case, we don't have to go to grams. So we can just figure out moles of ammonia in each case. So we've got 2.0 moles of nitrogen. Nitrogen is a 1. So I've got 1 mole of nitrogen and 2 ammonia. And so that is 4.0 moles ammonia. 2 times 2 is 4. And then I've got 5 moles of hydrogen. Hydrogen is a 3. And then ammonia is 2. NH3, 2/3. Two-thirds of 5. 3 moles of ammonia. So which one is our limiting reactant?
Hydrogen.
Hydrogen is our limiting reactant. How many moles of ammonia can be produced? 3.3. So this number, because that's the smallest of the 2, that tells us this was our limiting reactant. It also tells us that is how much can be produced. And so we solved number 1 and number 2 at the same time. Now let's do part B. Got 3.1 moles of nitrogen and 10.2 of hydrogen. Let's 6.8. Thanks. What is my limiting reactant? Nitrogen. This number is smaller than that one, and so that is my limiting reactant. How many moles of ammonia can I make?
6.2.
6.2. And that's that problem. So here is the bigger version, one dealing with masses, grams. And so we're starting with grams, and then part B is what is the maximum amount of aluminum chloride in grams that can be produced. And so when we do our 2 stoichiometry problems, we're going to go from grams all the way to grams, and we'll solve part A and B at the same time. So we're starting with 0.4 grams of aluminum is 0.6 grams of chlorine. Let's do the aluminum first. So I'm going to do that entire thing from left to right. So what is the molecular weight of aluminum? 27? Thank you. 27. And that is 1 mole of aluminum. We've got moles of aluminum. And we're going to our the other thing, our product, our aluminum chloride. Aluminum chloride is a 2, they're both 2s. What is the mass of aluminum chloride?
Yeah,
133.2. 133.2. If you do it, what does that come out to be? 2.22 grams of aluminum chloride. So we've got half done. Now we need to do the same thing, but with our chlorine. So we've got 0.60 grams of chlorine. This is 71. Chlorine is 35 and a half. There's 2 of them. That's 71. Chlorine. Whole. Chlorine. That's 2, 3. Exactly.
0.75. Oh,
0.75?
yes.
What is the limiting reactant? Chlorine is a limiting reactant. That's the smaller of the 2 numbers. That came from that. So that is our limiting reactant. What is the maximum amount of aluminum chloride in grams that can be produced? 0.75. What I see people do wrong here is, I don't know if they get lazy or if they forget, but what they do is they just convert the 2 grams into moles of the reactant. Whichever one is smaller, they say is the limiting reactant. You can't do that because it depends on the coefficients. It's possible that you could be starting with fewer moles of one reactant, but you need fewer. And so the one that you're actually starting with more moles of could run out first. And so you have to do the work. And so what we did is we went to grams in both cases to start with. We solved B when we solved A. What the slides did is they stopped at moles of aluminum chloride here and said, this is how much did they?
Why did they use the one with more?
When I go through these slides, a lot of times I don't look at what they actually did. What they did is the method that I told you not to do. And so I don't know if you want to put a note or something that if you look at that slide and it doesn't make sense, that's a good thing. That means you're doing it the way I want you to do it. Okay? But if you want to do it their way, that is how you would do it their way. That's the way where you have to think about what you have to do. So then, because they did it separate, different way, they had to go from moles to grams separately at the end. So these two slides, I would either cross them out or be aware that that is not the way I suggest that you do it. So the last thing we have to talk about is percent yield. Percent yield is easy. These problems aren't going to just have part A, what is the limiting reactant, part B, how much can you make. They're also going to have part C. And part C is going to say, if you do this reaction in lab and you make this many grams of product, what was your percent yield? Okay? So what a percent yield tells you is of the amount of product you are supposed to make, based on this, how much did you actually make in lab? And when you do a reaction in lab, you are never going to get 100%. If you got 100% exactly, that's sheer luck. Okay? It happened to come out as 100. You're not going to do a reaction in lab, you get 100%. And so what a percent yield is, like I said, is how much of what you were supposed to get did you. Almost always, your percent yield is going to be less than 100%. 100% yield would mean you got exactly how much the stoichiometry said you were supposed to get. What happens is reactions don't finish. We'll talk about why in maybe a month or so. That's a whole nother lecture. But most reactions don't actually go to the point that something runs out. And if they don't go to the point that the limiting reactant runs out, you don't make as much as you calculated. And so your percent yield is going to be less than 100%. If you get more than 100%, that means something is wrong with your reaction. Either you made a different product than you thought you were going to make, or a lot of times what happens is you have leftover reactant that is contaminating your product. And so when you weigh your product, you think you're just weighing aluminum chloride, but you're not. You're weighing aluminum chloride and the aluminum that didn't react. And so you have to purify your product from your excess reactant. And so when you find percent yield, when we do it, it's going to be in grams. But as long as the units of what you were supposed to get and what you did get are the same, the percent's going to come out the same. The math is the same. And so if they're both in moles, that's okay. If they're both in grams, that's okay. But they have to be in the same unit. And so the equation for percent yield is just how much you actually got divided by how much you were supposed to get times 100. So the actual yield will be given to you in a problem. It'll either be given to you in a problem or you're actually going to do something in lab and measure that. The theoretical yield is the stoichiometry. So in this case, our theoretical yield was 0.75 grams. If I said you did this in lab and you got 0.5 grams, your percent yield is 0.5 divided by 0.75 times 100 is 66.6%. 2/3. So that's all there is to that. You'll get to part C. It will say you ran this in lab, you got this amount. What is the percent yield? And you'll just take your answer from part B, which you took from part A, and divide the actual number given to you by your theoretical yield times 100, and you're done. So here is an example. This one, so this was not the full-on from grams to grams and then find percent yield. This one's a little bit shorter. And so it says we 0.2 moles of chlorine react with excess sodium. So that means we know that our chlorine is our limiting reactant. And so we don't have to do both sets. We can just do one stoichiometry problem, starting with our chlorine, to figure out how much sodium chloride we were supposed to make, and then compare it to how much we actually got, which was 0.4. So 0.20 mole, looks like owl. 0.20 moles of chlorine. And then we want moles of sodium chloride. And so our actual yield is in moles, is given to us in moles, and so all we need to do for our theoretical yield is calculate moles. We don't need to take that extra step to go to grams. And so I can stop here. So sodium chloride is a 2, chlorine is a 1, so this is 0.40 moles of sodium chloride. So what is my percent yield? In this case, it is 100%. My actual yield, it's actual divided by theoretical times 100. So in this case, the actual is 0.4. The theoretical is 0.4 times 100 is 100%. Is that the last slide? Oh, there's another one. So, okay, that's the last slide. Yeah, that's the last one. So I will save the point I was going to say for this. So this is the type of thing that you would see on an exam in its entire form. There's a reaction. In this case, it's written out in word form up here. You have the amount of reactant. You have the amount of product that you made. In this case, you don't have to figure out the limiting reactant. Again, it's straightforward. Just do one stoichiometry problem. So it says, what is the actual yield? What is the theoretical yield? What is the percent yield? So actual yield, what do we do to find that? Actual yield. It's given to us. That is the 7.44. So we are making aspirin. Aspirin is actually very easy to make. So we're making aspirin in the lab. Stoichiometry says that we should make 8.95 grams. We make it in the lab, we get 7.44. So our actual yield is 7.44. What is the theoretical yield? 8.95. And so how do we calculate the percent yield? 7.44, the actual divided by 8.95 times 100 equals something. 83.1%. In this case, you have to think actual divided by theoretical. Most of the time, it will be the small one on top, the big one on the bottom. But that is not always the case. If you got more than 100%, the big one is going to be on the bottom. So you do actually, in this case, have
to have more than 100%.
like either there's something wrong with your reaction, you made a different product than you thought you were going to make, or there's leftover reactant in your product. There's a reaction, I actually think it might be Thursday. I think it's Thursday. I would bet money that at least 3/4 of you will get more than 100%. And you're going to have to tell me why. Because if you get more than 100%, something has to be wrong. There is no way around it. Something has to be wrong. And you're going to have to tell me what is wrong. So in this case, percent yield was 83.1. Let me go back. So in this one, we calculated our theoretical, our actual was given to us, we found our percent yield. On an exam, you're going to have this multi-part question. A is what is the limiting reactant? B is how much can you make, which is the theoretical. Part C is what is your percent yield. There's partial credit available for all of them. So my suggestion, if you have no idea on that exam how to do limiting reactant, take a guess. There's probably going to be two reactants. If you guess right, I got to give it to you. Okay? So take a guess at your limiting reactant. If you don't know how to do the problem, finding the amount of product is probably out the window. But guess anyways. You're not going to get it right, but if you guess for part B and then use that as your theoretical for part C, you can still get full credit for part C. Even though your answer will be totally wrong, if you use the equation correctly with the theoretical yield you calculated and the actual yield that was given to you, I will give you full credit for that percent yield part. So if you're stuck on A, guess on A and B, and then calculate C if you remember. Even if you can't remember, and this applies to a lot of things going forward, write the equation for me. If you can write the equation, even if you can't figure out what numbers to plug in them, you'll get something for that. If you know the equation, at least write the equation. Are there any questions on today's lecture? Okay. I think, if I remember what lab we're doing right on Thursday, it's the mole one. I think what's included in that is essentially this. Yeah, because you're doing the post lab. Yeah. Yeah, and so you're going to do this in lab on Thursday, so hopefully that will really help you get your hang of this. Because you'll really see it working, and you'll do examples in the pre-lab and the post-lab. So let's go over last week's homework. Is there anybody that wants to do